Thanks for coming and yeah, I'm muted. So we actually just had a very excellent poster session earlier, half an hour ago, and then this is another new poster session focusing on this exciting topic, subduction zone. We know it's so exciting because we have such a diverse group of people trying to starting here. We have in total we have 9 presenters coming from 7 time zones. As you see here, I believe there are more time zones in the audience. So I'm Shawn Wei, by the way. I'm an assistant professor of seismology at Michigan State University. And this session is slightly longer than the previous one. It's going to be 1.5 hours. And before we start talks, I just want to briefly introduce the agenda and some rules that we have. This is the orders of the posters. We in total have 9 posters. They are already all online on that Pathable virtual webpage. And we are going to have 7 lightning talks. Each of those will be 2 to 4 minutes. And so during these talks, we hopefully have no interruptions. So please keep yourself muted. And then after that, we'll see maybe we can take a short break or not. And then we will have a Q&A session following that. So we will have nearly 1 hour for a lot of, I hope, constructive discussions after that. So because we have so many speakers and we have so many people in the audience here, so I hope that you can ask your questions in the chat window anytime so that I can keep a track who is the first one ask the question, who is the second. That's just easier. And you don't have to type in the entire question. You can say, okay, I have a question. Then you put your mark there. I can unmute you later. And I prefer that not to raise your hands virtually or physically for questions. Put your questions into chat. But if you have any follow-up, immediate comments, discussions on the current question we're discussing, then just use the hand raising function to do that. So that's what I prefer to have. And so I guess that's it. Then we can start. The first one is given by Leo MacLeod, who is an undergraduate student at the University of Washington, and looks like he found some very interesting events, short duration events from Cascadia data. So Leo, please take it away.
Great. Hi. So yeah, I'm going to talk about short duration events on the Cascadia Initiative Ocean Bottom Seismometer Array. Next slide. So what is a short duration event? So these are events that are occurring on individual instruments at a time that are unrelated to earthquakes and have this pretty like sudden onset. You can see an example there at the bottom from J73C. These events have been seen worldwide in many different environments. And there's a lot of kind of questions about what's causing them. Next slide. So there's kind of 2 main hypotheses that we have for the area. One is that the short duration events are being caused by methane seeps along the seafloor. And the other is that it's the result of biological activity, such as like a fish or crab or something along the seafloor running into the sensor. Next, okay. So our area of interest is the Cascadia Initiative Array. So for this specific part of our study, we were looking at stations on the continental shelf, the ones shown in red. And these were like generally above 1,000 meters. And so I'm going to specifically talk about 2 stations, J49C and G33D, which show sort of like a general pattern for each area. Next, okay. So for the study, we used obspy in Python to run a short-term, long-term detector for the year of data for each station, and then work to manually calibrate the acceptable amplitude by station. So looking at kind of a typical event and categorizing sort of what amplitude that was at, and then filtering all of our data so that it only included amplitudes sort of above a certain threshold to make sure we were making sure we were cutting out noise. So for results, J49C had this really interesting kind of daily pattern where at night the signal really dropped off, and so that was pretty cool to see. And this occurred on a few other stations in this sort of northern 2013-2014 deployment. I included another one on my poster, but the big part here is that we really see this amazing drop off at night. And then for G33D, we really don't see that. And for all the other stations that we've looked at so far in the southern 2014-2015 deployment, we don't see the signal that we saw in J49C and other northern stations. It's pretty consistent between day and night. So there's something else happening here. So in conclusion, we have evidence for short duration events being the result of biological activity for the 2013-2014 northern deployment. But the 2014-2015 southern deployment cause is more ambiguous. And it's very likely that there's a mix of events, but we can at least tie some of those to biological activity in the north versus in the south. There's something happening. And so moving forward, we want to run the rest of the stations on the shelf and then understand changes in local biota by different regions to see what could be causing this difference. And then we want to compare data from sensors in the Cascadia array to the buried sensors on the Ocean Observatory's Initiative cable array, because this will give us a good indication of where animals are, if they can actually run into the sensor, and if we see the same types of signals. So yeah, that's our work so far. Thank you.
Thank you. Excellent talk. I forgot to mention that Leo right now is studying both oceanography and also marine biology. And I hope you will find marine seismology is even more interesting. So next one is given by Brandon Shuck, who is currently a PhD candidate at the University of Texas Austin Institute of Geophysics. He's mainly studying the evolution of plate boundaries with active source seismic data. I'll take your time.
Okay, hi everyone. Happy to be part of this poster session. Great, yeah, so the research that I'm presenting in this poster is really targeting the process of subduction zone initiation. So trying to understand how subduction zones form and develop into mature plate boundaries. There's a little bit of an interesting caveat in that in the bottom left, it shows this diagram with all of our known plate tectonic forces, and slab pull, there's some research that shows that the slab pull force is by far the largest one. But if you don't have a subduction zone, then you don't have the slab pull force. And so that's not there, and that's something that needs to develop. So currently people are thinking about this in terms of two different cases, the vertically forced case, or whether forces are oriented horizontal. And there's different predictions for the kinematics of subduction initiation based on those two scenarios. So on the right is a diagram showing if you go the vertically forced route, the downgoing plate starts to sink nearly vertical and the upper plate starts to immediately experience extension. Whereas in the horizontally forced case, there's some net convergence between them and there's initial resistance and there's a time lag, and eventually the downgoing plate starts to sink and the overriding plate experiences extension. So we want to test the ideas about this transition to self-sustaining with some observations. Next slide, please. So these things are really hard to tease out if you look in the geologic record, but if you look at a subduction zone that's actively undergoing this transition, that's where you can get some really good insights. So on the left is a map of a seismic experiment active source that was done in 2018 that collects seismic profiles along the Poiseuille margin, which is located to the south of the South Island of New Zealand. So it's the northernmost segment along the Australian Pacific plate boundary south of New Zealand. And the history of basically the activity of the overriding plate tracks the stresses as subduction initiates through time. So I don't have enough details. We're looking at 4 structures in particular. So please come by the poster if you want to see the data and how we infer the different stresses. But in the bottom right is really showing from north to south the different evolution of stress over time. So this is just qualitative, red being compression, blue being extension, and subsidence as well. So you can, the two interesting things that we see is that the apparent magnitude of compression decreases from north to south, as well as the duration of this transition. So it's about 8 million years until you start to get a subsidence in the north, where it decreases to about 5 million years in the south. So it really is suggesting that where subduction nucleated in the north, it was under a lot of resistance, but actually once you look at a long strike, things got a little bit easier. So it's suggesting that propagating a subduction zone is a lot easier and faster than the initial site of nucleation. So go to the next slide, please. So that's really suggesting to us that this process is 4-dimensional, that a lot of the models are thinking about things in 3 dimensions. They have these 2D models and they run them with time, but you really need to consider the along strike effects. So in the left here is a summary diagram where the northern part of this subduction zone is in a self-sustaining state. We have slab melts that are coming out in subsidence of the overriding plate, but the southern part is still undergoing uplift and it's propagating to the south, but it's speeding up. So we think that there's some good evidence that this propagation is actually possibly going to continue along the entire Australian Pacific plate boundary. It's super exciting. I think Carolyn later on is going to talk about a segment a little bit further south and about the stage of subduction there. So this is kind of how subduction zones we think are starting in a small place and then eventually growing to, you know, something on the order of 2,000 kilometers long. And the horizontal forces are really dominating at nucleation, but vertical forces take over. And once it gets started, it's hard to stop. And that's really supported by the geologic evidence. So in the top right is the subduction zone initiation database, which shows all the new subduction zones that formed in the last 100 million years or so, so different events, and every single one of them formed nearby an active subduction zone. So just to conclude, it really suggests that subduction is the main driver of subduction. So I'll leave it there and happy to chat more about my poster with any of you. Thanks.
Okay, thank you. So the next one is a poster given by Florian Petersen. He is currently a graduate student in the final phase of PhD at the Jianhua Helmholtz Center for Ocean Research. And the research focus is on marine seismology in connection with the seafloor geology. And this is—
Hi, thank you for the introduction. So I present to you our, next slide. Oh yeah, right. So this is our study about the relationship between the seismogenic updip limit and the upper plate deformation at the erosional convergent margin northern Chile, so which is right now in review, and this as well in cooperation with the Universidad de Chile and Oregon State University. So for introduction, on 1st of April 2014, the Iquique earthquake ruptured a central segment. On the left, you see this there, which ruptured lately in 1877 with a magnitude 9 earthquake. So this event was preceded by a period of precursory seismicity, iseismic slip, creeping, and mainly ruptured towards the down dip region. And as well triggered not a significant tsunami in the Pacific Ocean. So 8 months after the main shock, we installed 2 temporary OPS networks. So in total, 23 months. And at the end of the last network in 2016, the Langseth as well accomplished to shoot a seismic array. And we use one of these lines, of these trench crossing lines here, the green line on the right side, to integrate this in our study. So next slide, please. So on the left side on top, you see the MCS data, and as well down there, the aftershock seismicity. And first as well, you can see, or we identify a strong decrease of reflection amplitude from the lower forearc to the middle forearc, and as well the correlation of the reflection amplitude from the plate interface with the onset of aftershock seismicity and the updip limit. As well, what's not really shown here is that this lower forearc, the higher reflection amplitudes correlates with increase of VPVS ratio of up to 2 in this region. So we interpret the striking of aftershock sequence as indication for subduction erosion, which occurs in the co-seismic and post-seismic phase. And these repeated co-seismic and post-seismic deformation forces extensive faulting of the upper plate. especially at the uptip limit. So next slide, please. So this is like a simple conceptual model, but this shows that when we follow these over time, so these, when we link the short-term deformation we see here now with the long-term deformation, what we see in the multi-channel seismic data, we can image the structure and the formation from hundreds and thousands of cycles. And over time, the tectonic erosion at the uptip limit forces to migrate the uptip limit landwards, mimicking the trench and volcanic arc migration. So, and this leaves a frontal weak wedge behind, which is likely to creep and is an R-seismic. So yeah, if you have any questions, come to my poster. And as well have on Monday and talk a bit more deep or in depth of this. Yeah, thank you.
Thank you. So before move to the next one, I just want to point out a technical problem. Someone reported that in the poster session, this is the web page. Sometimes you will realize that there's a loading error for certain posters. For example, this is Brandon's, which is a great one. But turns out you can find the file over here, and I guess the problem is that file is too large. It's if it's multiple like tens of megabytes, then there will be a loading error. But you are still encouraged to check those, to download those posters and also check this fantastic video. Okay. So now, okay, I guess it's my turn. Like I said, I'm a assistant professor at the Michigan State University, and I have to say this work is mainly done by my postdoc, Dongdong Tian, who is the first author over here. We're trying to talk about, look at the intermediate depth and the deep earthquakes in Tonga. So over here, this cartoon shows you the slab and also the Earth's deep water cycle. And we all know that the slab really plays a very important role in controlling this deep water cycle system. However, our understanding of the subductive slab is actually limited. And here I will argue that by looking at the intermediate depth and the deep intraplate earthquakes, and particularly stress drops, we can get some very useful information. Because stress drop, we know that this is one of the very fundamental characteristics of earthquake. It can tell us the stress state of the slab. It can even sometimes tell us the existence of fluids. The data I'm using is actually was collected more than 10 years ago when I started my PhD. And so over years, we have already identified more than 1,000 earthquakes. And over here, those are the red dots, and then the blue and the black symbols on these maps and the seismic stations. But here, I'm particularly focusing on four arc OBSs and 7 4 arc land stations. The reason is that we try to minimize the effect of complex attenuation structure in this complex system. So here, I just try to keep the methodology part very brief. We try to isolate source spectrum using a global spectrum decomposition method, and then we can get the corner frequency, and then based on that, we can estimate the stress drop. We are using a method widely used in Southern California, but we know that the subduction zone is different. Therefore, we have to make substantial improvements beyond that method that I'm gonna skip here. So these are our results. We in total get about 70% earthquakes resolved with the stress drop. This is, to me, is very encouraging, because if we are using other methods, we usually can only get like 10 or 20 earthquakes resolved with the corner frequencies. That's because the data quality, obvious data quality is low. But over here, you can see that these earthquakes are color-coded by stress drop. They vary along the Tonga slab, and then if we try to plot the smooth medium stress drop over here, you can easily find certain hot zones associated with the Tonga slab deformation. And then if we try to plot these stress drops against seismic moments and also against the earthquake, event depth, we found that larger earthquakes tend to have larger stress drop, consistent with previous studies, and we don't find a strong depth dependence of stress drop. But what's more interesting is over here, the Tonga double seismic zone. This is a paper we published a couple of years ago. That Tonga has the two-layer structure of this intermediate depth earthquakes form two-layer structure. And then this is the depth, slab normal depth distribution, and we can clearly see the upper plane and lower plane. When we try to plot the stress drops, it's interesting that the lower plane earthquakes definitely have much lower stress drops compared to the upper plane earthquakes. And remember, those earthquakes are in the inner part of the slab. So what does that mean? That could suggest a lower stress state due to slab unbending and also fluids. Alternatively, because we estimate stress drop based on an assumption of seismic velocity, if there's a low velocity anomalies in this region, then we can also have underestimated stress drop. So it's possible that there's a low. It's either fluids associated with these events, or there's a low velocity anomalies in the inner part of the Tonga slab, and this is actually related to the following following poster. And so the next one is given by Wang, who is currently a graduate student at Michigan State University, actually in my group. He's going to talk about some low velocity anomalies in Tonga.
Hello, everyone. Today I will talk about a deep low velocity layer in the Tonga slab. Subduction water cycle is quite critical for deep water budget and mantle dynamics. As you can see from the cartoon below, oceanic sediments, crust, and the mantle all can carry large amount of water into mantle. However, dehydration reactions will release water as the hydrous minerals are brought to deeper depths. It still remains uncertain on the maximum depth of the water delivered by slabs. Since the presence of the hydrous minerals usually show as a low velocity anomaly in seismic imaging, we want to use the seismic data recorded by the ocean bottom seismometers and the field land stations to image the depth limit of the potential hydrous minerals in the Tonga slab. Thanks for the great description of the Tonga slab in Shawn's talk. In this study, we want to provide some insight into the subduction water cycle by investigating this called end member of global subduction zones. Next slide, please. Since the direct P and S phase are usually dominated by the signals from the structure above slab, in this study, we are looking at the P to S converter phase at the slab surface. P wave travels long distance along the slab interior and converts to S wave when it comes across with the slab surface. This converted phase is very sensitive to the structure in the uppermost part of the slab, and it will provide a better image of the potential hydrous minerals. Because seismic signals are usually noisy from ocean bottom seismometers, we manually examine the P to S converted phases in both time domain and frequency domain. The upper right figures show an example of P to S converted phase identified from an OBS recording. The upper panel shows the seismogram in the time domain. The lower panel shows the spectrum by applying Fourier transformation. The green vertical line in the upper panel is the theoretical calculated P to S converted phase. The red vertical line is the identified P to S converted phase. We can see there is a very distinct energy 10 seconds after the P wave in the spectrogram, and it arrives later than the theoretical calculated P to S arrival time. This implies that there must be some low velocity anomaly somewhere along the real path. After we identify all the P to S converted phases, we utilize FM tomon to perform seismic tomography. The bottom figure shows the tomography results. You can see there is a very obvious low velocity layer imaged at the uppermost part of the Tonga slab. This low velocity layer extends to around 200 kilometers depth, and its amplitude is less than 8%. The P to S converted phase are very critical for our study, and we are trying to use machine learning technique to identify this phase more efficiently. Here is our advertise. So if you are interested, please visit Lucien's poster in the open poster section. Thanks. Next slide, please. This is the comparison of low velocity layer imaged in several subduction zones. The left figure is our result using the P to S converted phase in the Tonga. We can see that the low velocity layer can extend to around 200 kilometers depth. The upper right figure is the result in northeastern Japan. They also use the P to S converted phase to do seismic imaging. The depth limit is around 100 kilometers depth. The bottom right shows the results using direct PE waves in Hokkaido. The low velocity layer extends to around 80 kilometers. So the direct comparison of the depth limit of this low velocity anomaly shows that the Tonga slab can bring hydrous mineral to very deep depths compared with non-subduction zones. It will potentially improve our understanding of deep water budget by looking at the deep hydrous minerals in this cold-end member of global subduction zones. Thank you very much. I'm looking forward to your questions.
Okay, thanks. So the next one is a poster given by Steve Hicks and the Voiler team. And Steve currently is a seismologist at the Imperial College London, and he previously worked on this project in Caribbean. And take your time, Steve.
Thanks, Shawn. Hi, everyone. Good evening from the UK. So yeah, I want to move from the Pacific to the Atlantic in my brief talk, where I'm talking about the Lesser Antilles subduction zone. So this was an OBS, broadband OBS deployment for 14 months, was one part of the project. This is part of the Voiler project, which is a large consortium project involving multiple universities across the UK. These were instruments deployed in 2016 to 2017. Rob Allen is giving a talk tomorrow evening on the active source component of that, so I recommend having a look at that. So there's a number of authors and institutions on this, so take a look at the poster for more details on that. So next slide, please. So yeah, why the Lesser Antilles? Why are we looking in this sort of unusual subduction zone? Well, it's a global end-member subduction zone. The rate of convergence is very slow, about 2 centimeters per year. And so there have been lots of studies on Pacific type subduction zones, but we want to find out what's the main difference with compared to Atlantic style subduction, this very slow deformation. And we have multiple fracture zones being subducted in the area, which might theoretically comprise more water that gets subducted, which might affect the dynamics of the subduction system. There's also variations in sediment supply, which increases towards the south. And so we can test different models of what might affect this sort of very conceptual kind of understanding of how a subduction zone works in terms of fluid getting down through the entering this subduction zone through the slab and then being driven off the slab, causing melting in the mantle wedge, and then reaching volcanoes at the surface. So that was the overriding aim of this large project. And we also have nice comparisons we can make between the seismic structure and geochemical variations at the surface, for example, from eruptive magma. So I recommend you look at George Cooper's paper in Nature from last year for more information on this area. So yeah, we had 34 broadband ocean bottom seismometers, a mixture of scripts and lobster instruments from the Alfred Wegener Institute. And these were deployed across the ARC and 4ARC, and we had a very high instrument recovery rate. And we use local earthquakes here to image the attenuation structure. Next slide, please. So yeah, we use an attenuation imaging to try and map out temperature variations in the subduction zone, but also perhaps we can image melt and volatile content in the mantle wedge region. So this is a summary of the sort of average 2D structure across the area, the attenuation structure. So this is P wave attenuation, this is S wave attenuation. So this is inverse Q. So the pink to yellow colors are regions that are more attenuating. The blue areas are less attenuating regions. So the blue areas can be regarded as perhaps colder, drier areas, whereas the pinker regions are more warmer and or melt rich or contain volatiles. So what you can see here is we have the characteristic subduction zone structure. This is a cross section. So here we have the top of the subducting plate. You can see the high Q of the subducting plate. But we imaged the mantle wedge very nicely of the asthenosphere. particularly in QS, and it's more attenuated with the S waves than it is the P waves, which hints at significant shear wave attenuation. This line here is the interpreted base of the upper plate from receiver function. So you can see that the mantle wedge seems to, or the attenuating part of the mantle wedge seems to extend up to the base of the upper plate. And we see, sorry, that's an error there, that 1000, that should be 20. So we go down to 1000 over QS, so about 20, so we reach minimum values in the mantle wedge, which is actually quite low. So that's strongly attenuating given the relatively cold nature of the subduction zone. We also find that the cold for a corner actually extends kind of, this is the volcanic arc at the surface, you can see, and that extends actually quite deep and beneath the volcanic arc. So this is really unusual. We didn't expect to see this. This appears to differ from Pacific style subduction zone. So this might imply that we have a large slab to mantle decoupling depth in this sort of end member style subduction zone. And perhaps we have melt ponding at the base of the upper plate. So there's implications for how melt gets through the mantle wedge into the volcanic arc. Next slide, please. So that was the 2D structure that I showed before. We've also looked at the along arc variations in seismic attenuation. And so these are sort of map views plotted at 20 kilometers, 50 kilometers, 95, 120 for P waves on the left, P wave attenuation, and S wave attenuation on the right. You will see that for S wave attenuation, we reach a sort of minima in Q around this region. This is the island of Dominica at about 95 kilometers depth in the mantle wedge. And Dominica has had the largest volume of erupted material for the past 25,000 years. And there's also perhaps a nice correlation between the S wave attenuation reaching that lower value in that part of the arc, and also some geochemical constraints on sort of the amount of water in erupted magma. So there seems to be a nice correlation between Q and the volatile content as shown in magmas at the surface. But we don't really know why the mantle wedge is most attenuating here, why there appears to be perhaps more melt. Perhaps we've got some sort of lateral melt focusing. And also we can compare, we've had other studies on this area as part of the VOLAR project on looking at seismic velocities, both from local body waves and also from teleseismic surface waves. And we've been able to find some really nice correlations between Q and shear wave velocity. But we don't find such a nice correlation between Q and VPVS ratio, which is really interesting. That might highlight some sort of difference between melt and fluids in the mantle wedge. I'd love to hear your thoughts on that. So thank you very much.
Thank you. So this will be our last lightning talk given by Caroline Eakin, who is actually coming from the future, because right now it's March 12th at her time. Caroline right now is a seismologist and faculty member at the Australian National University, and she is actually giving us a recorded video.
Hello everyone, and good morning from Canberra, Australia. On behalf of my colleagues and collaborators listed here, I'd like to share with you some brief insights about our OBS deployment in the Southern Ocean around the Macquarie Ridge. But first, why am I presenting in a subduction zone session? The Macquarie Ridge, circled here in red, lies south of New Zealand along the plate boundary between the Australian and the Pacific plates, and it's thought to be one of the few locales in the world where subduction initiation may be imminent. Why is this? Well, if we look here at the earthquakes along this plate boundary, the Macquarie Ridge located here is associated with some of the largest underwater earthquakes in the world, not located in a subduction zone presently subducting. At the center of this ridge on the crest lies Macquarie Island, which has been deemed a UNESCO World Heritage Site based on its unique geology. It's composed of oceanic crust and mantle rocks and has been uplifted from the sea floor to several hundred meters above the surface in around the last 10 million years. In October last year, we went out and deployed 27 ocean bottom seismometers around Macquarie Island along the Macquarie Ridge on our either side. We're due to go back in November to pick them up, But this is a big and exciting project for us, as it's the first time in Australia that we've deployed the national fleet of OBS seismometers using the National Research Vessel RV Investigator. There's obviously many challenges to doing an OBS project to collect this kind of data, but I think there are some challenges that were specific to our project. This included operating in the furious 50s. Macquarie Islands is located around 55 degrees south, which meant we had lots of stormy weather, which at times we weren't able to work or to operate. All in all, we lost about 38% of our allocated ship time due to poor weather, but we were able to be efficient and deploy all of our OBSs in the time that we have remaining. Due to the Antarctic circumpolar current, we also have some of the strongest ocean currents on Earth, leading to up to 5 kilometers of drift from where we dropped the OBS to where it landed on the sea floor. As you can see in the bathymetry image, we also have incredibly rough and steep topography in this region, which limited the places in which we could put the OBSs. It also limited these regions mostly to the dark purple, which were smoother areas that happen to be very deep, with most of our instruments located below 4,000 meters. All in all, we're looking forward to going back and collecting these OBSs later this year in November. And I'm looking forward to hopefully coming back to this forum in future years to be able to share some of our new and exciting results. Thank you.
Okay, so this is the end of the lightning talk, but I still want to remind people that we actually have 2 additional posters in this session. And one is given by Hannah Tilley, and she is currently a PhD student at the University of Hawaii, working with Greg Moore. And you'll find a relatively longer video on the webpage for her poster. This is about segments in Nankai Trough. The next one poster is given by Jianhua Gong, who is currently a postdoc. She basically just finished her PhD from MIT Hui Joint Program, and then now she's a postdoc at Scripps Institution of Oceanography. And she is using OBS and the pressure gauges to try to study the plate interface near the deformation front. And please check her poster. I believe she has a PDF poster and also a longer video on her webpage. So, and I guess this is the end of all the lightning talks, but now let's move on to Q&A sessions. I want to reiterate the rules over here is that because we have so many presenters and I believe a lot of questions, so I prefer you put your question in the chat window. You can just say, I have a question, and then so that I can keep track who is the first one to ask to answer. But if you have some follow-up comments or discussions, you can just raise your hand. So let's go first. I think Jim, you want to ask? Jim, are you there?
Hi, Shawn. Do you mean Jim Garrity? If so,
oh yeah.
Yeah. Sorry, I don't know if I did something to indicate I had a question. I don't. Yeah, I don't at this point. I put something in the chat just that commenting on the remarkable drift that yeah, that they saw at Macquarie. I mean, that's pretty remarkable. But that's not a very interesting scientific point. So.
Okay, then let me see all the comments about that drift. I assume that's not a question. So Doug, do you have a question for Steve?
Yeah, Steve, very nice talk. My question is, what kind of QPQS ratio are you getting when you compare the 2 images? I was trying to do it in my head, but you've probably done it a little more systematically. And you know, if you have a relatively low ratio, then that can indicate bulk attenuation. Do you see any evidence of bulk attenuation?
Sorry, yeah, thanks, Doug. Good question. Yeah, so I haven't done yet a direct inversion for QPQS. That's on the to-do list. But yeah, if I just divide the two sort of models together, which is not 100% robust thing to do. Just looking at the numbers I get here, so I think I get about in the mantle wedge an average of 1.5, which I think indicates significant bulk attenuation, because I think global average is something like above 2, if I remember correctly.
Yeah, it should be like 2.4 if there's no bulk attenuation.
Yeah, we certainly get less than 2 everywhere.
Yeah, so that's not terribly different than what Shawn and I got in Tonga.
Yeah.
But we saw some spatial variation in that.
Yeah, I mean, given where the attenuating, or given there's attenuation going, or strong attenuation going all the way up to the base of the upper plate, I would expect that intuitively to be more melt than fluids there. So yeah, that would be kind of consistent with that interpretation, I think.
Yep, thanks.
Here, I assume you have different resolutions on these two images, right?
Yes, correct. Yeah, hence why, yeah, the division's not completely robust.
More questions? Just waited. So Caroline, why don't you just speak up, and well, it's better to have a live conversation.
Sure. Hi, everyone. It's 5 a.m. in the morning here, so I'm not putting my camera on. But there's a couple of comments about the OBS drift that I mentioned in my presentation, that we had up to 5 kilometers. The highest was actually exactly 4.8 kilometers of drift. And it was interesting to see people's comments as to how shocked, I guess, they were at that extent of drift. We were pretty surprised as well. I have a map in my longer presentation, but it was actually really difficult for the OBS deployments, because not only were some of them really large drifts, but the direction was also unpredictable, because there's these really strong eddies in the ocean currents when they hit the Macquarie Ridge and they interact around the island. Yeah, so we were sort of at the time of the deployment trying to sort of map this and try to predict it, but it was a big challenge for us in deploying the OBSs.
Okay, so I guess next is Megan.
Hi, yeah, I just have a general question about the slab 2.0 model. I've seen a couple people plot it, and it looks to me, I'm not that familiar with it. It looks to me that it plots a little bit above, a little bit more shallow than the actual seismicity. Is that a consistent observation in many subduction zones? And how was slab 2.0 made?
Yeah, for the slab 2.0 in Tonga, it seems that the updated model is quite above the seismicity. So actually, I'm not sure why this is happening in Tonga's region. So I think I see some figures in Alaska subduction. The slab 2 model seems to be good, and for the Jianhua Gong's poster, I think she also used slab 2 model at some point. It seems like this model is okay for the Cascadian subduction zone. Maybe it depends on different region.
Yeah, okay.
Can I jump in on that? Because we had a similar issue in the Lesser Antilles, where we found slab 2 was about, I think, 50 kilometers slab normal depth difference between what we inferred from the top of the intraslab seismicity. So I went in to investigate this and spoke with Gavin Hayes at USGS, who obviously led the Slab 2 project. So what they're doing is from the bottom of the thrust seismogenic zone, they're applying a constant taper to sort of bring the slab up from the bottom of the seismogenic zone, which is based on the age of the lithosphere of the trench, and also the thickness of the Wadati-Benioff zone. So what they're trying to do is to try and account for, or to try to put the slab, to put the Wadati-Benioff seismicity into the slab, and to account for that sort of the thickness variations due to age. We think that was an overestimate certainly for the Tilley subduction zone, and based on some thermal models as well. It'd be really hard to get the top of the slab sort of that shallow compared to the seismicity, but that's where it comes from. I think it might be a similar issue that other people are seeing in other subduction zones.
So in the northern Chile, we have another observation there of the slab 2 model. If you show my slide number 2, there's a seismicity like 3 kilometers above the slab 2 model. So, and the seismicity or the plane interface, you can infer from the seismicity as well correlates with the one slide, next one, yeah, there. The slab 2 model, the gray line here is below the actual plate interface, what we can image in the seismic data, in the Multichannel seismic data, and the seismicity, where the most of them is plotted there, it's a bit shallower then. So, yeah. But I guess this slab model is from the global catalog or from CSN, and these events are much deeper in the shallow subduction zone. So this is, I guess, from these depths.
In general, I think, just to jump in again, it's really interesting thinking about the intermediate depths. What is the top of the slab, and how do we define that? It's a really interesting question, because these models are driving, lots of geodynamic models and interpretations from passive seismology. So it's a really interesting question going ahead as to how we can think about what defines the top of the slab once it gets below the seismogenic zone.
Sure. I think Doug has a question for us. Doug, you're muted.
Yeah. I have a question for Fan or Shawn. Really nice observations. So how do you estimate the thickness of the low velocity zone? And previous studies that have seen the low velocity zone at the top of the slab, some have interpreted it as the crust only, very narrow, and others have interpreted it as, a wider region into the mantle. And how are you going to constrain the thickness?
Yeah, very good question for this. For our study, we have performed some restoration tests, like to put a different thickness of lowest layer inside at the uppermost part of the slab, and to see if our data can resolve, this lowest anomally. It seems like if we put like a lowest layer that have a thickness of 20 kilometers, it can also be reviewed by our dataset. So we think that the lowest layer imaged in Tonga should be more than 20 kilometers thick. So so it means that the hydration state of the Tonga slab may extend very deep into the slab mantle, not only the slab crust.
Mm-hmm. Okay, thanks.
But I have to point out, right now we are still just using ray theory to do the tomography. So it would be important for us to use some like finite difference simulation or something to see to look at it, because eventually it's a waveguide. So we're not, well, we need to test how robust this thickness is. Thanks.
Do you retrace the rays then as you recompute the models?
Yeah. We
Okay.
do. In each iteration, we update the model and redo the real tracing for the station and event pairs.
Mm-hmm. And I noticed there's kind of a gap in the slab in your starting model, and if I remember, some previous models of Tonga also showed this kind of gap. Is that why you put it there? And is your result sensitive to the kind of gap between 100 and 200?
Yeah. Because right now our initial model have this kind of the velocity around 100 to 200 kilometers per second is not so strong. So we want to make sure this low velocity we imaged after we use the PIS converted phase is from the low voltage layer, not from our initial model. So we plot this to clarify this low velocity structure.
And here, this input model is basically James Conner and your model, but we also tried some other study models like Texas global model or gap model.
Yeah.
And so do we have more questions? So Brandon, do you have a question or comment?
Yeah, it's a question for Caroline. I'm just wondering about the geometry of the OBSs that they deployed, and if she thinks that, yeah, it would help sort of relocate earthquakes along other segments of the plate boundary. I know, like certainly when I look at the seismicity data on Voyager, like the depths are basically not constrained at all because the geometry of where the stations are at on New Zealand. So I'm wondering if the experiment will allow for a better understanding of seismicity along the entire plate boundary, or is it mostly just gonna be like focused around Macquarie?
Thanks, Brandon. So the array was designed to study the seismicity on the Macquarie Ridge segment. So I don't know how much more helpful it's going to be for the other segments, because all your instruments are going to be, if we're talking about for the Pusager, all the instruments are going to be south of that area. So I don't think it's going to get good locations for those events, but certainly if there are events, it will record them as well, and maybe it might help a little bit, but I don't think it's going to help a lot for the other segments. That is further north.
Yeah, thanks. Were there also, just as a follow-up, I'm curious if the bathymetry data showed anything new about whether under thrusting appeared to be predominantly from the east or from the west?
I don't think there's any conclusions on that yet, but yeah, so I think Mike Coffin and Joanne Stock are sort of leading that in terms of the interpretation. So you might like to talk to them, but yeah, I haven't heard any discussions on that yet, but we'll be working on it.
Great, looking forward to it. Thanks.
Thanks.
And Megan, do you have a question for Steve?
Yes, I was just looking back on the lower left figure. There are two vertical axes labels that I don't see. You're plotting frequency and something. Yes, that one. So I see, what are the two, the left and right vertical axes labels?
This for me? Yeah.
Yes.
Which plot are you
The lower left.
Sorry, Shawn. Yeah, sorry, I just realized you almost shared my slides. Yeah, so good question. So this is basically drawn from Kate Reichert's 2009 paper from her study on the Costa Rica Nicaragua subduction zone. So yeah, the left-hand axis, sorry, yeah, it's come off. That's Q, QS in this case, and the right-hand axis will be 1000 over Q. So yeah, we're getting Q of about 50, or minimum Q over Q equals 50 in the left-hand figures, or 1000 over Q equals 20. So that shows where we lie with respect to some other subduction zones.
Okay, and that's QP or QS?
This is QS, yeah.
QS, okay.
Apologies, yeah.
Yeah, and then, I'm sorry, so did you compute temperature estimates then? Did you use a Q temperature relationship?
Yeah, so this is sort of just a broad comparison, but what we've done specifically, which I focused on a bit in the poster itself, is we've generated some geodynamic models based on kinematic modeling for the Lesser Antilles. So we've predicted Q from empirical experimental relationships like the Fowler and Jackson type experimental studies. So we found that the Lesser Antilles is more like the mantle wedge is about 1,200 degrees C. That's about as warm as it gets. So to get down to those low Qs, we need to add in some volatiles or melt really into the mantle wedge. We can't explain them through temperature alone.
Okay. And then I just have a general question for everybody, because I just forget all my metamorphic petrology. But when you talk about melt, the difference between melts, and this goes for ridges or back arcs, when you talk about hydration, dehydration, and melt, how does that present chemically? When we talk about water in the mantle, are we talking about OH or free hydrogen? Is it OH in certain minerals that dehydrate? And then we talk about melt, are we talking about melt on grain boundaries? Can you just sort of talk about that generally? My brain's a little rusty. Anyone can educate me on that, please.
I guess because seismologists really don't have a conscious way to call these things. It depends. Steve, do you want to answer?
Yeah, I mean, for our geodynamic models to put water into the mantle wedge, we talk about OH, concentrations of OH. But in terms of distinguishing melt versus water, depends who you, what you can distinguish from attenuation versus velocity, depends who you talk to. So if you talk to Jeff Abers, for example, he will be fairly adamant, I think, that attenuation should be seen melt more than water, or at least hydrated mantle wedge. So it's likely to be melt, in his opinion, and based on some paper from a few years ago. So, yeah, but it's definitely up for debate, which is why I always say could be fluids and or melt.
Okay, so the Q, the attenuation, is more sensitive to melt, whereas the velocities are more sensitive to hydration or water. Is that
I
what
guess
you
there's
mean?
no conclusion, right?
Yeah, I mean, yeah, one thing I mentioned one thing we've noticed from our paper, so a colleague from Karlsruhe Institute of Technology is producing a seismic velocity model for the Lesser Antilles subduction zone using local body waves. And yeah, we see a weird sort of offset between QS and VPVS ratio. So the VPVS ratio, yeah, the slide up here. So the VPVS ratio is high, just above the slab, at about 140 to 150 kilometers depth. But you can see the QS actually reaches sort of a minimum higher up. So there's that like depth offset between VPVS and Q, which is really interesting to think about. Could it be water or hydrated mantle versus melt?
Okay, thank you.
Okay, I have a question for Leo, and so I'm really interested in this detected events. I have no background of oceanography or marine biology. So is there any sort of maps or other information you can compare with existing data in oceanography or marine biology that any correlation there?
So I haven't really done a in-depth look at this kind of thing yet.
I
So
don't think I can hear you.
oh, can you hear me now?
I can hear him.
Maybe it's
Yeah,
my problem.
Uh-oh.
Okay, go ahead.
I don't know if I should just keep. Okay. Great. Well, so I haven't really had a chance to kind of do like an in-depth look yet of different things. My current thoughts are to kind of look at changes in chlorophyll concentrations between the 2 years, because that could be an indication of sort of where there might be more or less biological activity between the 2 years that we're kind of looking at. also potentially looking at trawl data for the two areas, because that could give an idea about what organisms are living in those places. So if there's a lot of like crabs or bottom feeders, that might be a more useful sort of metric. But I'm still kind of thinking about what would be the best way to kind of compare data throughout the coast.
Thank you. Here, I just want to remind people that there are still a few posters which are not showing at the lightning talks, but they are still posted on webpage. I encourage you to take a look. And then my following question is actually for Jianhua Gong, and this is the try to look at the converted phases at Cascadia. So I think, Jianhua, I think I have listened to your talk a couple of days ago at the SSA meeting, and at that time you only show land stations, but right now it looks like you are getting some OBS data. So how different this, and just in terms of data quality or in terms of any tricks, do you think, is there any special processing you have to do in order to detect the PS and the SP phases at the OBSs?
Sure. Can you hear me? So can you hear me? Oh, okay, good. So we're looking for we're looking for like two types of converted phases, P2S and S2P, and for the P2S converted phases that generate from the slab interface, you could directly observe them on one of the horizontal components, like the top row figure in section 3. Here we show the P2S converted phases on two OBS stations. These waveforms are aligned by P wave, and they are sorted by S minus P travel time difference. You can see that on the OBS station, on the horizontal component, the P wave is very, very weak. And we have to align the waveforms based on the P wave on the vertical component. But I think the P2S conversion phase are relatively clear, but the quality of the data really depends on the station. Some stations are less noisier, but some are more, some are much noisier. Like for this case, FS 09D has a better quality than FS 16D. For the S2P converted phases, maybe, for S2P converted phases, because we observe on the vertical component, and one of the challenges that on vertical component, you also observe the water reverberation phase. And we use this method called wave field decomposition to remove the water reverberation using both the seismometer and the pressure gauge. So that's the basic idea.
Okay, thank you.
Yeah.
So I think this is a question actually already solved. So basically just two papers. Are there more questions? As I mentioned, this session is a little bit longer than the previous one. We still have like 25 minutes to go. Of course, we can end earlier and then to get a beer. It's a long day. Well, usually we bring beer to post the sessions, right? But
I have a question for Steve, I guess, and it may be a pretty ignorant one, but it really struck me as a little bit surprising as somebody who hasn't really looked at the attenuation structure in the arcs very closely, that what I think of as a really cold system like the Tilley system would be so highly attenuating, and therefore you're inferring pretty large quantities of melt. And I guess, was that something that was surprising to you guys? And what do you think is controlling that?
Yeah, really good question, Jim. Well, Atlantic lithosphere is very different to Pacific lithosphere. So this is it's formed at a slow spreading ridge, very different structural style, with the sort of the way the faults are formed, and you have things like core complexes, detachment faults. So there's potentially a way of getting more water down into the subducting plate. So yeah, as you say, it can't be based on the cube measurements we're seeing. You can't. It can't be explained just by temperature alone. So you have to get some sort of melt or volatiles into the system. I guess what's sort of surprising is that how the melt seems to be appears to sort of be, or it's a speculative interpretation that melt seems to be ponding at the base of the upper plate. Now the question is that, and it's offset laterally from the arc. So the question is, how does that melt eventually get into the arc? Does some melt sort of just get stuck there? Does it freeze in? Is a really interesting question, because yeah, we've got this big sort of cold part of the mantle wedge, and then laterally offset from that, we've got the attenuating part of the wedge, offset from the arc. Interestingly, the arc has migrated sort of back and forth over the last 50 million years or so. Rob Allen, who's on the call at the moment, has done some really nice work on that. So I'm wondering if we're sort of seeing partly a signature of this, maybe the way the arc has migrated back and forth, and has sort of allowed, it's sort of focusing the melt in different ways, and there's maybe allowing this cold mantle wedge corner to maybe accrete or shrink with time, or it's just a feature of how just the slow convergence works in some ways, and also probably the lower, or the greater amount of water, particularly deep in the subducting plate compared to Pacific style lithosphere. So that's the best explanations we've come up with so far. Yeah, it seems like the attenuation agrees with the shear wave velocities really nicely. There's a nice correlation, but the shear wave velocities are not abnormally low compared to what, for example, Shawn sees in Tonga, Laos. So the Q is abnormal, but the S waves, shear wave velocities are not, but they do broadly agree with each other. So yeah, no true answer. Yeah.
I have a very quick follow-up question before Ming asks. Just Steve, so, I just don't know how active here the back is. Is that possible to have any magma or volcanism at back? Any melting there?
Yep, that's a really good question. So we don't think there's any recent back arc spreading in the Antilles. So this is again work that Rob Allen's done. But it seems like the melt is sitting sort of where we might expect some sort of back arc to form, right, or some sort of back arc axis. So it's an interesting question as to maybe at one point the back arc did try to spread, but now the melt's got stuck there. But how that's still showing up as sort of an attenuation anomaly is a really good question. But yeah, no active back arc spreading that we can see at the surface, and based on the sort of the shallow geophysics and active source that Rob's been working on. No sort of recent magnetic data or any magnetic data. The magnetic data don't support that we would have back arc spreading. Rob, feel free to jump in if you want to give a more detailed answer.
Yeah, so I can maybe comment a little bit on the back arc. So in the north, where Steve's profiles are, the back arc of the Lesser Antilles, the crust is very thick and there's no back arc spreading whatsoever. So the crust in the back arc there is maybe 25 kilometers thick, and there's debate as to whether that's from some kind of oceanic plateau or as a result of a very long period of volcanism. The one place in the Lesser Antilles where you might have back arc spreading is in the south of the back arc, in the south of the Granada Basin. But that kind of sits south of the area that Steve's tomography shows. And even there, the most recent phase of back arc spreading was something like 40 million years ago, probably.
Okay, thanks. Then Ming, do you have a question?
Yes, I didn't see any of the poster yet. However, I have a question regarding the attenuation in terms of QS and QP, because these two types of attenuation, they derived from different frequency range, right? And different waves too. And then how are you going to even compare these two types of, two values, which very likely sampling different length scale and also even physics. And is there any like meaningful comparison to just compare QS and QP, like this quality factor?
Yeah, that's an excellent question. And of course, the shear waves are so attenuated, you really lose your bandwidth to be able to do to sort of fit the T star and get a corner frequency from. So yeah, S waves are tricky, particularly when it comes to ocean bottom seismic data. But we were lucky to even get some signal in some ways. We weren't sure whether we would. So a sort of a formal QPQS inversion is sort of certainly helps with sort of data and damping issues and different resolution issues. That's on the to-do list for me, but maybe we could, I don't know if sort of spectral ratios might help, maybe not. It sort of helps to get rid of the corner frequency issue. But yeah, there's lots of assumptions made. Maybe Shawn has more experience with these sort of issues. Maybe wants to jump in.
Yeah, I want to make a comment. So first of all, these are both body waves, body wave P, body wave S, and then at least for our work in Tonga, when we try to invert for T star, we have already considered the frequency dependence of attenuation. Of course, that's a very poorly constrained value, but still we try different like 0.27 or 0.3 or even 0.6 for the alpha value. So and we basically just correct everything to the reference frequency, which is usually 1 Hertz. And we also, you are right. When we talk about the QP/QS ratio, we have to be extremely careful. Then there are a lot of tests to verify whether the QP/QS ratio is really meaningful. And I think we have done some tests in our low basin project. Is if we underestimate the QP/QS, if we underestimate the frequency dependence, then the QP/QS ratio will tend to be larger, not smaller. So if we observe even smaller QP/QS ratio, that's unlikely to be a result of the frequency dependence of attenuation. And so this is one thing, but you are right. Generally speaking, P and S waves are sampling different frequency, but think about velocity tomography. They always do VP, VS tomography. They are still sampling different frequency ranges, but I guess they have P and S waves, at least for attenuation, have some shared frequency band. Usually, I believe that's 1 to 3 Hertz in subduction zone regions. So I think still it's tricky, but still doable.
Yeah, that's good explanation. However, with full waveform right now, we are able to use the same frequency band, and however, it still cannot resolve the problem that the coverage is different in terms of the P and S, right? Even you resolved that attenuation, frequency dependent attenuation part, we still cannot resolve the data coverage part.
What do you mean by data coverage? Oh, well,
it means for the same region, you don't even have the same coverage.
Usually, if people try to do the QP/QS ratio, then we have to. You mean there will be way more P wave measurements than S wave?
Yeah, in general.
So we basically just get rid of all the extra P waves. So we always use a pair of P versus S wave.
Oh, that's a good solution. That's for sure. So the resolution test has been done for QP and QS. They are proved that QP and QS can be resolved at the same length scale that you can trust, right?
Well, I guess so. What I showed earlier, Doug Weens asked the question about, what's the QP/QS I see in the Tilley. So that was just a simple division of the P wave over the S wave model, because I haven't done that formal inversion yet. But when I do the formal inversion, we take the station pairs, so the station event pairs where we have a P wave observation and an S wave T star observation. and then we will invert for QPQS ratio directly. So that on its own, we would have a resolution estimate just for QPQS ratio on its own without thinking about is it Q or is it S or is it P.
Okay, that's also pretty cool. And also, what about QSV and QSH?
Yeah, if anyone wants to shed any light on attenuation anisotropy, yeah, it's a good question. Yeah, I don't know. So I use the transverse component to maximize the signal to noise ratio. So I don't think about whether there could be anything on there, any sort of anisotropy of attenuation.
Jim, do you have a comment or question?
Yeah, I'm intrigued by this whole conversation of comparing QP and QS. And it comes from a perspective from like long period surface wave normal mode perspective, where both of those things, so under the underlying attenuation processes are either bulk attenuation or shear attenuation. And shear attenuation is generally orders of magnitude lower than bulk attenuation. And so it's the only term that matters. And if I remember correctly, VP and VS are both written in terms of bulk attenuation and shear attenuation. And so it makes me wonder whether could you be inverting, would it be useful to invert both data sets for that underlying shear attenuation and just constrain that really well and determine physical processes associated with that? Or is bulk attenuation in fact important for body waves? I guess the implication that QP and QS would give you different results suggests that that must imply bulk attenuation is important for body waves.
Did you mean a joint inversion between Q and V? Is that what you were hinting
Joint
at?
inversion between Q and P for the underlying Q mu as opposed to QP and QS.
Yeah, it would be cool. We could do it, yeah.
Yeah. Actually, Doug and I had the paper last year, published last year, just focusing on QPQS. We sacrificed resolution. We throw out most of P wave measurements, and then just focusing on the pairs that have been always having P and S measurements. Yeah, I guess that's a very strong evidence of bulk attenuation over there. But I guess yeah, your suggestion is very good. But I guess so far there hasn't been many conclusive studies on bulk attenuation yet. Then I really hope community will be more inspired by these observations, and then even rock physics community can spend more time on like experiments looking at bulk attenuation. I guess.
Yeah, one more thing regarding, I guess James already touched upon the intrinsic attenuation and the apparent attenuation, right? For that part, so how do you distinguish these two? Or so far, I know that probably VAD did something about the intrinsic and or apparent attenuation, but nobody else ever like really touched upon that kind of topic. At least with I have only limited knowledge on this, so maybe Shawn has some idea.
There are actually a lot of papers on trying to distinguish scattering attenuation versus intrinsic attenuation, especially for people who are working on crustal attenuation. That's probably a different community, but for that community, low QPQS ratio is never a problem because they always see this low QPQS ratio in crust, but that is usually just a result of scattering. But on the other hand, once you know local elastic heterogeneity, you can somehow simulate scattering attenuation. And that's the approach we use to isolate intrinsic versus scattering. But there's another way, I think, by looking at the envelope of waveforms. I think there are multiple groups using that. Then I'm not expert on that, but basically just by looking at the envelope drop of P, especially P wave waveforms, you can also just instantaneously invert for scattering and intrinsic attenuation. But that, my understanding, requires very high quality, very high data quality.
Yeah, even with very high data quality, sometimes you experience focusing, defocusing effect due to the geometry of the sedimentary basins. And that's what Colin Dalton observed, even with long period, high quality waveform data. So in this case, how are you going even to take that into account, especially in a region where you do have very thick sedimentary basins?
But usually for body wave attenuation, because the frequency is high, and my understanding is usually we don't really worry too much about the focusing, defocusing, but scattering is a big problem.
Yeah, and I guess to follow on something Shawn's done in his papers as well is to look at spectral residuals at certain stations to see what are you fitting with sort of the T-star you've been able to find, and if you find some systematic variations, spatial variations between those residuals and the locations of stations, you know, those sitting in the back arc versus those sitting on the fore arc or on the island, then you might be able to say that there is a hint of the shallow crustal structure on the spectra. But I've not been able to find that for the Antilles, and I think Shawn didn't find that for the Tonga Lao area.
Just because I know really little about attenuation, and I don't know what kind of frequency of S wave you are using compared to P wave, how different they are.
So it depends on sort of the amount of attenuation, I guess, and the amount of signal you get. So for me, a station on the fore arc recording P waves, you could get between 1.5 hertz and up to 20 hertz in places, up to the Nyquist. For an S wave observation on a station in the back arc, where we see more attenuation coming up through the mantle wedge, we could be just a width of 1.5 hertz or 2 hertz up to 4 or 5 hertz. So that bandwidth really decreases when those paths are sampling more attenuation in the mantle wedge, for example.
Yeah.
Thank you.
Well, this becomes very attenuation-oriented discussion. But do we have more? We have more exciting posters. Do we have more exciting questions, discussions?
I guess. Can I ask a quick question to Leo? Sorry for jumping in. Yeah, I think I've seen similar signals on our OBSs when I've just been like checking manual pics of like local earthquakes. So have you? I didn't quite. Maybe you did mention this in your presentation poster, but have those signals been reported elsewhere in different areas, or is it just been focused on sort of with Cascadia to start with?
Yeah, so we know about them because they are just found all over the place, and there's a lot of different ideas about what's going on. So specifically, our lab and our area of interest was in Cascadia, but yeah, they are a worldwide phenomenon, and a lot of people are working to try to figure out what's causing them. And there's a lot of debate about could it be local biology, and some people put cameras down and were like, okay, does this work? And some saw creatures and some didn't, and it was sort of a mess all over the place of what's going on. So yeah, they definitely show up everywhere.
Yeah, they've definitely messed up or thrown off the automatic picker for local earthquakes for me.
Yeah.
Really important to find out what they are.
Yeah.
I'm also wondering, because the asthenosphere beneath the slab, it's also quite interesting, right? And I only see, is there any study that has that kind of data coverage that can image the attenuation beneath the slab, at where that slab actually bends?
Yeah, I mean, from local earthquakes, they don't see the subslab asthenosphere, so you'd need to use probably teleseismic observations. I know Caroline's been involved in sort of looking at anisotropy from mantle beneath the slab, so it might be able to answer, but I don't know about attenuation from my point of view.
Yeah, it would be nice to see the differences in terms of attenuation. If it's because presumably they are different material, right? Or the dehydration from the slab that caused the melt in the mantle wedge, or the asthenosphere is certainly something different. And I just want to know if the composition of the volatile or even the rock itself, what kind of impact on the attenuation that is imaged either with P wave or S wave.
So I guess Zach Alon had a paper from a couple of years ago looking at the the oceanic plate attenuation before any subduction in Cascadia and the Iquique Ridge. So that might be an idea to look at from the teleseismic side. Yeah, from the local earthquake side, I don't think we can see it. That's one paper I know of. So yeah, I think there's a few studies looking at the attenuation of oceanic lithosphere before subduction. That's another field really. But during subduction, I don't know of any.
Yeah, well, we need more attenuation studies. And I guess we are close to time. The end of this session, and thank you all. And if we don't have more questions, I think we can conclude this session. We have heard a lot of exciting discoveries and also very constructive conversations over here. So thank you all. And don't forget the post session in, I believe, half an hour, right? So good. See you soon.